Hi everyone, welcome back. In this session, I am going to finally give you the formula for Black-Scholes model for valuing call option and put option. In the previous session, I didn't give you any formula, but I showed you that the value of an option under Black-Scholes is equal to the value of an option under binomial tree, where the number of time steps in a binomial tend to infinity. Okay, we saw that through the Derivation software. Now I'm going to finally give you the formula for Black-Scholes formula for the formula of Black-Scholes call option and put option. It is, first, let's start with the value of a call option. Value of a call option is equal to C0 is nothing but value of a call option. C0 or value of call can be denoted as VC is spot price into ND1 minus present value of exercise price into ND2. It is spot price into ND1 minus present value of exercise price into ND2. In this whole equation, you already know two terms. One, the spot price. I don't have to explain that, which is nothing but 170 in our question. Okay. And two, you know what the present value of exercise price is. Okay. Present value of exercise price in our case, with exercise price was 160. Okay. The present value of exercise price is nothing but 160 divided by e power RT. Remember, we are using continuous compounding. So here also the present value is going to be done on a continuous basis. Okay, it would be some 160 divided by e power 0.035. Okay, because it is 0.07 into 6 by 12. Okay, you will get some answer. Anyways, so we know two terms. We do not know what ND1 is and we do not know what ND2 is. Okay, apologies, give me a second. Okay, I will explain what ND1 and ND2 are, but after giving you the formula for value of a put option. Okay, value of a put option, P0 or VP or value of put is equal to present value of exercise price into N minus D2 less spot price into N minus D1. If you actually do a comparison between the value of a call option and the value of a put option, S into ND1 was the first term in value of a call. That has become a part of the second term in value of put. The difference being here we have used ND1, here we have used N minus D1. Okay. In the value of a call option, present value of exercise price into ND2 was part of the second term. That has become the first term in value of a put option, with the difference being ND2 has become N minus D2. Okay. Have absolutely no complications with regard to this. I think this should be an easy part and a straightforward part to remember. Value of a call option is S into ND1 minus present value of exercise price into ND2. Okay. You have to by heart the value of a call option. All that you have to do is basically invert it for value of put option. Present value of exercise price becomes the first term multiplied with N minus D2, and that is, and you from that you reduce spot price into N minus D1. Okay. So please just keep this a little straightforward. The dirty part of Black-Scholes is going to come after this. Okay. This is absolutely not the dirty part. This is, if you ask me, this should be considered to be the easiest part of Black-Scholes model. Okay. Now let us come to the formula for D1. The formula for D1 and D2. But before that, I will just tell you ND1 is normal table distribution value or the normal distribution table value for D1. Okay, basically for those of you who know what normal distribution is, what we do is we just go and find out the value of D1. Okay, D1 is like Z. Okay, we find the value of D1 and we find out the corresponding probability for D1. Okay, that probability is nothing but ND1, and ND2 is normal distribution table value for D2. Okay, ND1 and ND2 actually have meanings. I will let you know, I will give you the meaning of ND1 and ND2 after I'm done with all the formula, after we actually finish solving the sum that we had in our hand. After that, I will tell you the meaning of ND1 and meaning of ND2 also. Okay. So ND1 is normal distribution table value for D1. ND2 is normal distribution table value for D2, and similarly n minus D1 is going to be normal distribution table value for minus D1, and n minus D2 is going to be normal table distribution value for minus D2. Okay, D1 is, I mean, if D1 is 2, minus D1 is nothing but minus 2. Okay, I mean, that is how you can basically interpret it. Okay, minus D1 is nothing but minus of the value of D1, right? So ND1 and ND1, ND2, N minus D1 and N minus D2 are basically normal distribution table values for D1, D2, minus D1 and minus D2. Okay. Now coming to the formula for D1. This is a little dirty part. Ln of S by E plus RF plus sigma square by 2 into T, the whole divided by sigma root T. This is the formula for D1. Okay, it is ln. Ln refers to natural log of S by E. Okay, I am doing S divided by E, where in our case S was 170, E was 160. Okay, ln of 170 divided by 160 plus RF plus sigma square by 2 into T, the whole divided by sigma root T. Okay, this is the formula for D1. Okay, D2, you're lucky, you can just remember D1 minus sigma square root of T. Okay, the formula for D2 is straightforward. It is D1 minus sigma root T. Okay, this was the dirty part that I was referring to. Okay, this is that whole dirty part that you need to remember. Okay, I will tell you how to remember also. How to remember is going to be through hard work. I'm not going to give you any smart option. Okay, this is the formula that you need to remember as part of D1 and D2. And this is the value of call option and the value of put option. Okay, so basically there are 4 formulas that you need to remember, but out of the 4 you need to primarily remember two formulas. One is the value of a call option and the other is formula for D1. Okay, because formula for D2 and value of put option, they're actually not something that you need to by heart. Okay, and I'll tell you how at least I by hearted this as a student. Okay, as a student, what I used to do was, so what I used to actually do was every day I used to take my own numbers as a student and continuously for a period of 10 days, I actually solved Black-Scholes equation. And every day I used to write this equation down. Okay. The biggest problem is the first time when you write the equation, you will remember it. Okay. But you will remember it only for that minute. Okay. 7 days later, if I touch you on that equation, you will forget the formula for D1. You will remember probably the formula for value of call and value of put, but you will forget the formula of D1. Okay, so what I did was continuously for 10 days, I took my own numbers and I solved for the value of D1 and I solved for the value of call option and put option. The best thing is you can actually calculate, I mean, you can actually cross verify your answer with the answer as per original Black-Scholes using the calculator that we saw. Okay, using the Derivation software, you know what the answer should be. You calculate the answer on pen and paper after writing this formula, and believe me, after 10 days or after the 7th or 8th day, you will never forget. Okay, I will never forget the formula of D1 for my life. I know that. Okay, because I did that for 8 to 10 days and I remember it. You wake me up during my sleep and I will tell you the formula of D1. Okay, even now, when I write the formula of D1, I don't look at the formula somewhere and then write, right? Okay, so just do that for a period of 7, 8 or 10 days, and believe me, after that you will remember D1. And all you need to do is spare about 10 or 15 minutes in the night or in the morning, up to you. All you need to do is spare 10-15 minutes in the night and then work on create your own numbers and work for the value of a call option and value of a put option. Cross verify your answer with the answer of the answer as per the calculator. Okay, and then you can also every day you can keep changing the value of t. Like for instance, someday you take t as 1 year, sometimes you take t as 0.5. You keep changing all the numbers, tried having different combinations and stuff. Okay, so like I would say that is my advice. Okay, so basically this is the formula for D1 and this is the formula for D2. Okay, now let us actually solve the sum that we had in our hand. Okay, I'm still not giving you the meaning of ND1 and ND2. Okay, I'm just telling you that ND1 and ND2 is some value. Okay, Now let us solve the sum. I will that we had it in our hand. So the spot price was 170, strike price was 160, RF was 7%, standard deviation was 18%, right? And time to maturity was 6 months or 0.5 years. Agreed? Now we start off with calculating D1. That is the first step. Okay. D1, again, I'm writing the formula. You also write along with me. Ln of S by E plus RF plus sigma square by 2 into T, the whole divided by sigma root T. Okay. Which is equal to Ln of 170 divided by 160 plus RF is 0.07. RF is 0.07 plus sigma square is nothing but 0.18 square by 2, the whole multiplied by T. T is nothing but 0.5. It should be in years. Okay. T is 0.5. The whole divided by standard deviation, which is 0.18, square root of 0.5 again. Agreed? Ln of 170 by 160 for the CFA and FRM candidates, obviously you can calculate it using your calculator. Okay, but for CA final students, the value of ln will actually be given in the question. Okay, it is 0.060625. Okay, I will stop with 4 decimals. It is 0.0606. Okay, and then I have plus the part in the brackets is going to be 0.0862. This is 0.0862 into 0.5, the whole divided by 0.18 into 0.5 square root is 0.1273. Okay, 0.1273. Okay, so that is equal to 0.0606 okay, D1 is equal to 0.8146. Okay, this is the value of D1. D1 is equal to 0.8146. Okay, D2 is equal to D1 minus sigma square root of T. Okay, D1 is nothing but 0.1273. Sorry, D1 is 0.8146. Apologies. D1 is 0.8146. Sigma root T was nothing but the denominator in D1, right? The denominator in D1 is 0.1273, which means D2 is nothing but 0.8146 minus 0.1273, which is equal to 0.6873. This is the value of D2, 0.6873. Okay, D1 is equal to 0.8146, D2 is equal to 0.6873. So first I would like to show you how to calculate the value of ln in Excel. Okay, so you have a function in Excel called ln. Okay, equal to, if I press equal to ln, it calculates the natural log. Okay, the ln that we wanted was ln of 170 divided by 160. Okay, 170 divided by 160. Ln of 170 divided by 160 is nothing but 0.0606, which is what I wrote here as well, 0.0606. Okay, so that is how you actually calculate the value of ln. All right, in Excel. Now we have D1 and D2, and I told you that ND1 and ND2 are nothing but normal distribution table value for D1 and normal distribution table value for D2. Okay, so I will now bring up the normal distribution table value, or alternatively, let me actually first show you how to calculate it in Excel, and then I will show you how we can also find it out using the table. Okay, so in Excel we have a function which is called norm s dist. Okay, normal standard distribution, norm s dist, where the only input that you need to give is the value of z. Okay, you need to give the input as value of z, and for us z is nothing but D1 and D2. D1 we got it as 0.8146, so I'm writing 0.8146, and if I press enter, it is giving me a value of 0.79. Okay, 0.79 is nothing but probability. Okay, this is ND1. Okay, Similarly, ND2 also I can find out using norm S dist, and the value of D2 was 0.6873. Okay, value of 0.6873 is 0.75, which means the probability is 0.75 or 75%. Okay, in a normal distribution table, what you basically try to find out is the probability. Area under the curve is nothing but the probability. Okay, so ND1 is 0.79, ND2 is 0.75. Okay, so let me write that down as well. ND1 is 0.7923, ND2 is 0.7541. Okay, ND1 is 0.7923, ND2 is 0.7541. Let us also go ahead and calculate N minus D1 and N minus D2. N minus D1 is actually nothing but N of minus 0.1846. Agreed? It is nothing but N of minus 0.8146, right? And N minus D2 is nothing but N of minus 0.6873. Okay, because D2 value was 0.6873 plus 0.6873, minus D2 is nothing but minus 0.6873. Okay, let us solve it using Excel. Norm is this is minus 0.8146. Agreed? Minus 0.8146, and this one is minus 0.6873. Norm S this is minus 0.6873. Okay, it is 0.20 and 0.2459. Okay, let me write it. 0.2077 minus this is 0.2459. Okay, N minus 0.8146 is 0.2077, N minus 0.6873 is 0.2459. Okay, if you actually notice, this is N minus D1, and this is N minus D2. Okay, if you actually see, ND1 plus N minus D1 is actually going to be equal to 1. Similarly, ND2 plus N minus D2 is also going to be equal to 1. Not approximately, it is going to be exactly equal to 1. Okay. Okay, it's going to be exactly equal to 1. So actually, we will not find the value for N minus D1 in this fashion. We will straight away write N minus D1 is equal to 1 minus ND1, and N minus D2 is equal to 1 minus ND2. Okay, I think this becomes basically easier. Okay, I will tell you later on why they add up to 1. Okay, there is a logic as to why they actually add up to 1 as well. I will tell you the logic later on. Okay, so basically we have to remember that N minus D1 is nothing but 1 minus ND1, N minus D2 is nothing but 1 minus ND2. Okay, so it is enough only if you calculate the normal table distribution value for D1 and the normal table distribution value for D2. Okay, I showed it to you with Excel. Now let me show it to you using the normal table format that you actually have, that actually appears in an examination as well. Okay, this is basically the table that you actually receive as part of your examination. Okay, if you actually look at it, the way it needs to be read is you have Z values. Okay, you have Z value of minus 3.9. The second decimal of Z is on the top row. Okay, so this particular row needs to be read, this particular cell needs to be read as corresponding to minus 3.9. This is minus 3.91. This is minus 3.94. This is minus 3.96 and so on. Okay, for instance, this one is minus 3.33. Okay, that is how this cell needs to be referred to. Okay, so you have values of Z. Okay, it is ranging from minus 3.9 to plus 3.9, and you have the second decimal as part of the top row. Okay, and what you have in these in between is actually probability. Okay, probability that Z will be less than this value. Okay, the probability that the actual variable of Z will be less than minus 3.9 is going to be 0.4 times 0's 5. Okay, so this basically refers to probability, and that is the reason if you see probability is going to range from 0.00003 to 0.99997. Okay, because probability can only be positive, it cannot be negative, right? So you have all these numbers ranging from 0 to 1. Okay, so this is the value of Z. The second decimal is on the top row, and what is in between is actually the probability. Okay, and D1 and D2 that we have calculated is similar to Z. Okay, D1 and D2 is Z, and what we are basically doing is we are inputting the value of Z and finding out the probability. Okay, we are using the value of Z, okay, and finding out the corresponding probability. For instance, the value of D1 that we got was 0.8146. Okay, it is 0.815. You can read it as 0.815, right? Okay, now I'm basically scrolling down. I'm moving to 0.8. Okay, this is 0.8 and our value is 0.815. Okay, 0.815 lies actually in between 0.81 and 0.82. Okay, I don't have the third decimal on this paper. I have only up to 2 decimals. Okay, 0.81 and 0.82 is what I have, and our value is actually 0.815. Okay, so if you actually take the average of these two values, okay, I'm just taking the average of these two values, 0.79103 plus 0.79389 divided by 2 is 0.7925. 0.7925 is the probability, and the value that we got as ND1 is actually 0.7923. Okay, of course there's going to be a rounding difference because I've rounded this off to 0.815, right? Okay, so it's approximately correct. Okay, similarly we had D2 value of 0.6873, or we can consider this as 0.69. Approximately it is 0.69. Okay, so let us look for 0.69 Z value. This is 0.6. 9 is basically the last column. So 0.69 probability, or the probability corresponding to a Z value of 0.69 is 0.7549. Okay, and we got 0.7541. Okay, so that is how it must be read in a standard normal distribution table function. Okay, but I will be using primarily Excel because that is more convenient. Okay, I don't have to really look for these numbers and stuff, but this is how you actually read the Z table. Okay, we have over here we have minus 0.8146. I'll just show it to you of how to see for a negative number also. We have minus 0.8146, which is almost minus 0.815. Okay, minus 0.815 means I need to search for minus 0.8. Okay, this is minus 0.81 and this is minus 0.82. Okay, you take the average of these two, that will be minus 0.815, which is nothing but 0.20897 plus 0.20611 divided by 2, you have an answer of 0.2075. You have an answer of 0.2075 and we had 0.2077. Okay, basically you can calculate n minus d1 as 1 minus nd1 also, but I'm just showing you that even if we calculate the normal standard distribution table value of minus 0.8146, we will still get the same answer. Okay, that is what I actually wanted to show. So now if you actually see, we have all the inputs that are required for valuing the call option and all the inputs that are required for valuing the put option. Okay. So now let us actually put it into the facts that we had. Okay. And we'll calculate the value of a call option as per Black-Scholes method. Okay. The value of a call option is S into ND1 minus present value of exercise price into ND2. Agreed? S is nothing but 170 into ND1, we calculated it above as 0.7923. 0.7923 minus present value of exercise price is nothing but 160 divided by e power 0.035 into ND2 is nothing but 0.7541. Okay, this is nothing but 170 into 0.7923, which is equal to 134.69 minus the present value of exercise price is 154.50 into 0.7541. Okay, that is equal to 134.69 minus 116.51. Okay, 134.69 minus 116.51 is actually 18.18. Okay, we have an answer of 18.18, and if you remember, the Black-Scholes calculator gave us an answer of 18.199 something. Okay, so it is approximate, but the only, we have basically rounded it off, and that is the only reason for the difference. Otherwise, we've got the same answer as the Black-Scholes calculator. Agreed? Okay. So now let us calculate the value of a put option as well. Put option is equal to present value of exercise price into n minus d2 less spot price into n minus d1. Okay, present value of exercise price is 1. I can actually take it from above where I valued call. It is 154.5, right? 154.5 into n minus d2. N minus d2 is 0.2459. Spot price is 170 into n minus d1, which is 0.2077. Okay, and now if I calculate it, 154.5 into 0.2459 is equal to 37.99 minus 170 into 0.2077 is equal to 35.31. And if I calculate the value, it is 2.68. Okay, this is as per ours, and as per the Black-Scholes model, it is 2.70. 2.70. Okay, it is almost equal. Again, it is only because of rounding that there is a difference of 0.02, but it is almost equal. Okay, so I have shown you that when you solve with pen and paper, also the answer is the same as what we got as per the calculator. Okay, if we quickly revise, the formula number 1 that you need to remember is this: value of a call option is spot price into ND1 minus present value of exercise price into ND2. Present value needs to be calculated using continuous compounding, okay, or continuous discounting. Value of a put option is present value of exercise price into n minus d2 less spot price into n minus d1. Although this is not a formula, I'm just writing it down. Okay, that is second formula. D1 is ln of s by e plus rf plus sigma square by 2 into t, the whole divided by sigma root t. Okay, this is the formula for D1. D2 is D1 minus sigma root t. Okay, D2 has an alternate formula also. I will show the alternate formula on PPT. The only change is it's going to be exactly the same as D1. This plus will become minus. Okay, that is an alternate formula of D2, which we will not be using anywhere. The only places I will be showing you is when I show you the logic for Black-Scholes model. You know, I will be making use of the D2 formula to show you that the formula of D2 is actually being used somewhere. Okay, that is the only place where the formula for D2 is going to be useful. Otherwise, this is sufficient for examination purposes. Okay, the extended formula of D2 is not relevant from an examination viewpoint at all. Okay, so this is the third formula that you need to remember. D1 equals to ln of s by e plus rf plus sigma square by 2 into t, the whole divided by sigma root t. This into t is applicable to rf plus sigma square by 2. Okay, it is applicable to rf plus sigma square by 2, and that is why I've inserted these brackets. Okay, that is the third formula that you need to remember. And the last one is basically ND1 and ND2. They're more from, you just have to look at the standard distribution table value. Okay, this is the fourth formula that you need to remember. N minus D1 is nothing but 1 minus ND1, and n minus D2 is nothing but 1 minus ND2. Okay, so that you actually save some time instead of actually looking for the probability in the standard distribution table for n minus 0.8146 and n minus 0.6873. Instead, you just look at the values for ND1 and ND2, and 1 minus ND1 and ND2 will give you n minus D1 and n minus D2 respectively. So 4 formula to remember, 1 complicated formula only according to me, which is this one. Okay, and I've also given you how to actually by heart it, right? Okay, by heart it refers to, yeah, I don't like using that word, but yeah, you have to actually remember it. Okay, but remember, I'm going to give you the logic for Black-Scholes using delta hedging, risk neutral, and portfolio replication. in the subsequent videos. Okay, I mean, although it might look completely just formulae over here, I will be explaining you the logic for it under the subsequent lectures. But before, I'm not winding up this lecture, so please don't close your books. Okay, I am going to explain you the meaning of ND1 and meaning of ND2 and the meaning of N minus D1 and N minus D2. Okay, if you actually, okay, let me just ND1, okay, we have 0.7923. Okay, I'm coming to the Excel file, I'm going on call option and I'm clicking on calculate. Okay, if you actually see, you have delta over here. Okay, like I said, you have all the option Greeks over here. Okay, one of them is actually delta. If you actually see, delta value is 0.7924 and that is what we got as ND1. ND1 is actually nothing but delta of a call option. Okay, ND1 is delta of a call option, and delta, if you remember, I hope you do, means if the share price changes by $1, if the underlying share price changes by $1, how much will the call premium change by? Okay, delta of 0.79 means if the share price increases by $1, the call option premium is going to increase by $0.79. If the share price decreases by $1, the call option premium will decrease by $0.79. Okay, that is the meaning of ND1. So ND1 basically refers to delta of a call option, and delta refers to sensitivity of a call option premium to the changes in share price, to $1 change in share price. Okay, and remember, so the meaning of, or let's say, so let's say we have a stock price of 170. Okay, if the stock price goes up from 170 to 171, which means the share price is basically increasing by $1, the call option premium will approximately go up from 18.2 to 18.99. Okay, because the current share call price is 18.2, it will go up by 0.79, which means it will become 18.99. Okay, but that is going to be an approximate change. Okay, remember, just like how in fixed income we say that modified duration is an approximate change in bond price for a given change in YTM. Similarly, delta is also an approximate change. In bonds, you basically take the impact of convexity. Over here, you actually take the impact of gamma. Okay, anyways, that gamma is all part of option Greeks, which is not part of CA final syllabus if you ask me per se. It is part of CFA level 2 and FRM part 1, where we will be learning about it as well. Okay, so delta basically means if the share price increases by $1, how much will the call premium go up by ceteris paribus? Okay, that is the most important thing, assuming nothing else changes. Should I actually show it to you? Okay, remember 18.2 is the call premium right now. I am increasing it by $1. I'm increasing it to 171 and I'm pressing calculate. Remember, the call option premium will be approximately 18.99. Okay, I'm not going to say that it will be 18.99. There will be some amount of difference. Okay, I'm pressing calculate. It is 18.998, which means it is actually $19. Okay, there is a difference of 0.01. Okay, so delta actually calculates an approximate change in call option premium. And if you have noticed, delta has also changed. Okay, delta has also increased with an increase in share price. Okay, so delta itself keeps changing when the share price changes. Okay, now I am not going to get into that completely as to what that change in delta is and everything, because I will be showing it to you later when we interpret the Black-Scholes model, but I don't want to deviate too much right now. Okay, but I'm just showing you. I didn't have any intention of showing it also, but since we actually calculated and the delta changed, and some of you might have noticed it, that is the reason I'm just giving a passerby reference that the delta itself keeps changing. Okay, delta is not constant. Okay, the change in delta is what is measured by gamma. Okay, that's it. I'm not going to mention anything beyond this. Okay, and similarly from 170, if you earlier it was 170, right? It is 18.19. Okay, if I decrease the share price by $1, it will come down from 18.19. I mean, it will reduce by 0.79. Okay, let me just quickly do it. If the share price is made 169 and I press calculate, it is 17.41, whereas the answer should have been 17.4. Okay, because 18.19 minus 0.79 is 17.4. Okay, but the answer call premium is 17.41. Okay, so that is again an approximate change what we calculated. And if you again notice over here, delta has basically decreased. It has decreased from 0.79 to 0.78. Okay, anyways, so I've shown you what the meaning of ND1 is. Okay, ND1 is nothing but delta of a call option. Okay, let me write that down. ND1 is delta of a call option. Okay. Next, ND2 is probability that call will get exercised. Okay, ND2 basically represents the probability that a call option will get exercised. Okay, if I scroll up, ND2 over here in our answer was 0.7541. It means that there is a 75% chance that the call option that we are talking about will get exercised on maturity, and there is a 25% chance that the call option will actually lapse. Lapse meaning the share price is going to be less than the strike price. Okay, so the other way to put it is there's a 75% chance that the share price will remain above 160, and there is a 25% chance that the share price will remain below 160. Okay, at t equal to 6, obviously. Okay, that is the meaning of ND2. Okay, ND2 refers to the probability that a call will get exercised. Okay, and let's imagine actually you have a call option and a put option. Over here we had both call and put option for the same underlying whose share price currently is 170. Okay, at t equal to 6, if you actually imagine, both call and put cannot end in the money. Okay, only either the call will end in the money or a put and will end in the money. Of course, both of them can lapse if the share price is unfortunately 160. What I mean to say is there can be three possibilities. Okay, one at t equal to 6. There are three possibilities at t equal to 6. Share price is greater than 160, share price is less than 160, and share price equals 160. Okay, if the share price is greater than 160, call option gets exercised, but put option gets lapsed. If share price is less than 160, call gets lapsed and put gets exercised. Okay, here both call and put get lapsed. Agreed? Okay, so when a call option gets exercised, I'm not talking about this rare circumstances. Okay, this is actually a rare circumstance. I'm not talking about that. What I'm saying is, if call option gets exercised, the put option will lapse. If call option gets lapsed, a put option will get exercised. Okay, both call and put cannot get exercised at the same time. Agreed? Okay, so now what I'm just saying is, ND2, if it is the probability that a call will get exercised, then this has to be equal to probability that put lapses. Agreed? Okay, because if you're saying that ND2 is the probability that a call option will get exercised, when a call option gets exercised, a put option has to lapse. Agreed? Okay, because over here, if you see this scenario, if a call option is getting exercised, the put option has to lapse. There cannot be a case where call is getting exercised and put is getting exercised. Okay, so that is the reason I'm saying that ND2 is not only the probability that call will get exercised, it is also equal to the probability that a put option will get lapsed. Okay. Next, I told you that n minus d2 is equal to 1 minus nd2. Agreed? N minus d2 is 1 minus nd2. Agreed? If you actually think of it, a put option can either get exercised or it can get lapsed, right? A put option, now just think of a put option. It can, there are only two cases. A put option can get either exercised or it can get lapsed. Okay. ND2 refers to probability that put lapses. Okay. N minus D2 refers to probability that put option gets exercised. And that is the reason we are actually doing N minus D2 as 1 minus ND2. Reason being, the probability of put getting exercised and probability of put getting lapsed, the sum total should be equal to 1. Agreed? A put option can get either exercised or it can get lapsed. Okay. The sum total of probability of a put getting exercised and put getting lapsed should be 1. Okay. Therefore, we are actually saying that ND2 plus N minus D2 should be equal to 1. And N minus D2 is basically being calculated as a differential number as 1 minus ND2. Okay. N minus D2 is being calculated as a balancing figure as 1 minus ND2 because the sum total of both of these has to have a probability of 1, right? Because there cannot be any third situation. Either a put option gets exercised or a put option gets lapsed. And the probability of both of these happening should be equal to 1, okay? Because these are exhaustive events, right? Okay, so the probability should be equal to 1. N minus D2 represents the probability that put is going to get exercised. And we have calculated that as 1 minus probability that put lapses, okay? Put lapses or call exercised. And obviously, without saying it, you should realize that probability that put getting exercised is nothing but call getting lapsed. Okay? Because again, put getting exercised means that call option has to get lapsed. There cannot be a situation where both call and put actually get exercised. Agreed? Okay, so I have given you the meaning of ND1. ND1 refers to delta of call. ND2 is probability that call gets exercised. N minus D2, which equal to 1, which is equal to minus 1, 1 minus ND2 is equal to probability that put option gets exercised. What is left is N minus D1. N minus D1 is actually nothing but minus delta of put option. If you remember, delta of a put option is actually negative. Okay, delta of a put option is actually negative. Okay, always because the delta of a put option is inversely related to share price. Because when the share price increases, the value of put option falls. Okay, therefore the delta of put option is always negative. But I'm saying N minus D1 is minus of the delta of put option, which means it is actually minus of minus something, right? Minus xxx, and that is equal to plus xxx. Agreed? For instance, in our case, we had N minus D1 as 0.2077. N minus D1 was 0.2077. Okay, so what I'm saying is 0.2077 is equal to minus delta of put option, which means delta of put should have been minus 0.2077. Okay, if I move the minus onto the LHS, delta of put option should have been minus 0.2077. Let us actually come to the Black-Scholes calculator and see that the delta was minus 0.2077. I'm going to put and I'm pressing calculate minus 0.2076. Okay, it is approximately the correct answer. Okay, so N minus D1 is minus delta of put option. Okay, N minus D1 is minus delta of put option. And if you remember how we actually calculated N minus D1, we calculated it as N minus D1 is equal to 1 minus ND1. Agreed? This I'm telling you is minus delta of put. And this is delta of call. And if you remember, delta of call plus absolute value of delta of put should actually be equal to 1. Okay, absolute value of delta of put is actually nothing but minus of delta of put. Okay, because delta of put is negative, and when you do minus of delta of put, you get a positive number, right? So delta of call minus delta of put is actually equal to 1. Okay, the way we actually remembered it is delta of call plus modulus value of delta of put should be equal to 1. That is how we learnt it. Agreed. Okay. But the delta of put itself is negative. Okay. So modulus value of delta of put means nothing but minus of delta of put, right? For instance, if delta of call is 0.7, the delta of put will be minus 0.3. Okay. And the way this will hold good is 0.7 minus of minus 0.3 should be equal to 1. Okay, because 0.7 minus of minus 0.3 is plus 0.3. Okay, so delta of call minus delta of put is actually equal to 1. Okay, and if you see this, this equation has come from this part. Okay, if I retain minus delta of put on the LHS and I take this to the RHS, it becomes 1 minus delta of call, right? So minus delta of put is nothing but n minus d1. ND1 is nothing but delta of call. So minus delta of put is equal to 1 minus ND1. Okay. So here now, basically I'm making two statements. One is delta of call plus modulus value of delta of put, or absolute value of delta of put should be equal to 1, or this is also delta of call minus delta of put should be equal to 1. Okay, you might think that I'm making absolutely rubbish statements because over here I'm writing plus and over here I'm writing minus, but please remember that over here along with plus I put something called as modulus. Okay, when you modulus of a negative number makes it positive. Agreed? Okay, so that is the reason I'm saying delta of call plus modulus value of delta of put is equal to 1. And in the second case, I'm saying delta of call minus delta of put is equal to 1. It is, so this equation, n minus d1 equal to 1 minus nd1 has come from the second equation where delta of call is actually nd1. This is nd1. This, including the minus signage, is actually n minus d1, okay, equal to 1. So we are calculating n minus d1 as 1 minus, this is going on to the LHS, RHS side. So n minus d1 is equal to 1 minus nd1. Okay, that is how we are calculating. Okay, so 4 statements that you have to remember are these. Okay, and let me just probably erase this. I think it will be sufficient if I just write minus delta of put. Okay, so this is another thing that you have to remember. Nobody is going to ask you in the question examination probably, but it's good to know. ND1 is the delta of call. ND2 is the probability that a call option will get exercised. N minus D2 is the probability that a put option will get exercised. Okay, this tick mark refers to exercise. N minus D1 is minus delta of put. Okay, and if you see, these two are actually used in valuing call option, and these two are used in valuing put option. Okay, because these are basically put based values, right? N minus D2 and N minus D1 are both based on put and they are used for valuing put options. These two are based on call and they are valued based on call options. Okay, so this is the last thing that you have to remember. I think I'm done for this lecture. I don't think I have anything else to let you know, but let's quickly have a look at the PPT. Okay, I've managed without doing the PPT for this. So here we are. The value of a call option is S into ND1 minus present value of exercise price. K is exercise price. I actually could not insert all these notations of, divided by sigma square root T and all of that. So that is the reason I copied it from somewhere. And the place where I copied it from, K was denoted as exercise price. Okay. So present value of exercise price, K into e power minus RT is nothing but present value of exercise price into ND2. Put option, present value of exercise price into n minus d2 less spot price into n minus d1. Okay, where d1 is ln of s by e is exercise price or k, plus r plus sigma square by 2 into t, the whole divided by sigma root t. Okay, this multiplication of t is applicable only to rf plus sigma square by 2. Okay, d2, like I said, the only change is minus over here, nothing else. Okay, I'm just rubbing that off because I don't want that. The only change is minus over here. Everything else is the same as D1 formula. This can also be arrived as D1 minus sigma root T. Okay, for examination purposes, it's going to be sufficient. If you remember D1 minus sigma root T, this I've only kept because when I show you the Black-Scholes model as per risk neutral method, I will show you that there is some usage of R minus sigma square by 2 into T. Okay. ND1, like I said, refers to the normal table distribution value of D1. Okay, D1 is similar to Z, and ND1 is basically calculating the probability. Okay, ND2 refers to the normal table distribution value for D2. Okay, and we saw the formula for N minus D1 and N minus D2. Okay, the second thing is basically what I wanted to emphasize on was Black-Scholes actually makes a lot of assumptions, okay, which I will not be telling you all of them, which I will not be telling you right now. I will slowly introduce all those set of assumptions as and when I feel they are relevant. And at the end, I will make one video where we are going to see all the assumptions of Black-Scholes. Okay. So until then, I will not tell you what the assumptions are. I will be introducing them in between whenever relevant. Okay. Next thing that is applicable, that is actually relevant is Black-Scholes model actually works only for European options and does not work for American options. Okay. And if you remember, even in the Black-Scholes calculator, in the drop down, we had drop down for binomial European and binomial American, but we didn't have a drop down for Black-Scholes American. Okay. The reason being Black-Scholes is not applicable for American options because American options are actually path dependent. Okay, they can be exercised sometime in between. Okay, unlike European options are only concerned about what the share price will be on maturity, whereas American options are going to be concerned what the share price will be in between as well. Okay, if you remember where we actually have, give me a second, I will bring the other Excel sheet on the screen. Yeah, in European options, what we actually did was European call option. What we actually did was we calculated the payoff at t equal to 6, and we basically just calculated the expected payoff, discounted it to t equal to 3, and again calculated the expected payoff and discounted at t equal to 0. Okay, so the share price in between, actually 186, did not have any significant role to play for valuing the call option. Okay, what was only relevant was the share price at t equal to 6. Okay, of course you might say that the share price at t equal to 6 was derived from the share price at t equal to 3, but I'm not talking about that. All I'm saying is the payoff for a call option is dependent on share price at t equal to 6. Okay, and we are discounting that expected payoff into today's terms. We have not used 186 and 155 anywhere for valuing the call option directly. Okay, whereas if you remember in an American option, we used to ensure that the value of a call option in the middle at these nodes is at least equal to the intrinsic value of the call option. If it was not greater than the intrinsic value of the call option, we used to basically cancel this number and actually input the intrinsic value, right? Okay, we used to override these numbers with the intrinsic value because otherwise there would be an opportunity of arbitrage, and to prevent arbitrage, the value of an American option in between should at least be equal to its intrinsic value. Okay, the value should be greater than or equal to the intrinsic value of an American option. Okay, so we used to actually be concerned with the share price in between also. Okay, but what Black-Scholes does is it does not look at the share price in between. It straight away looks at what the possible share price could be at t equal to 6. Okay, and it discounts the payoff from the option to today's terms. Okay, it is not concerned with what the share price is going to be at t equal to 3 or any point of time in between. Okay, and that is the reason Black-Scholes cannot be used for American options. I will show it to you in much more detail when we again do the risk neutral method for understanding BSM. It will be much more clearer to you. Okay. When the Black-Scholes was actually initially introduced, it was one of the assumptions was that it is applicable for non-dividend paying stocks. It is applicable for stocks which do not pay dividends. Okay, but later on they came up with a modified formula for Black-Scholes where they basically tweaked some of these values, very small tweak. Okay, and then they said that the modified formula will then be applicable for dividend paying stocks also. Okay, I will basically be taking a separate session on dividend paying stocks. Okay, it is I won't be covering it as part of this lecture, but I just wanted to tell you that all these formulae are relevant for non-dividend paying stocks. And the last thing is derivation of the above formula. I will share a video as part of the description, although I don't feel it's relevant. I don't think you need to know it. Okay, I will share the description of I will share the YouTube description of a video which is available. You can see the derivation in your own interest. But my recommendation is it's not needed. You're not going to achieve anything by seeing the derivation. The more important part is the interpretation that we are going to do as per all the three models. Okay, I will be showing you how Black-Scholes formula of this formula can be interpreted for all the as per all the three methods that we already learned. I think that is more important than learning the derivation. Okay. This is n of x function. Like I said, n of x is nothing but x is nothing but a normally distributed value variable with a mean of 0 and standard deviation of 1. Mean of 0 and standard deviation of 1 is nothing but z. Okay, z has a mean of 0 and a standard deviation of 1. Okay, so we input the value of z to calculate the probability, and probability is nothing but area under the curve. This highlighted portion is area under the curve, which is nothing but probability. Okay, ND1 and ND2 are actually probability estimates. And this is ND1 is nothing but delta of a call option, and minus N minus D1 is delta of put option. Okay, I told you that N minus D1 is minus delta. Other way of saying it is minus N minus D1 is delta of put option. Okay, and N minus D1 is equal to 1 minus ND1, because delta of call plus the absolute value of delta of put is equal to 1. Okay, this is what we actually saw. ND2 is the probability that a call option will be exercised. N minus D2 is the probability that a put option will be exercised. Okay, and for one strike price, if a call gets exercised, the put option lapses. For the same strike price, you cannot have both call and put being exercised at the same time. Okay, so that is the reason we have N minus D2 equal to 1 minus ND2. Okay, like because N minus D2 is the probability that a put will get exercised. A put getting exercised is nothing but call getting not exercised. Okay, so call getting not exercised refers to 1 minus ND2. Okay, so N minus D2 is equal to 1 minus ND2. Agreed? I think that is it. In the next session, we will be seeing how to interpret the Black-Scholes model as per replicating portfolio. Okay, that's it for this session, guys. Thank you so much. Bye.